Welcome back. This is Steve Scully. I am reading from my book, The Instruction Manual, as it is written in the Cosmos, and we're picking up in the first section of Chapter 3, the structure of infinity. So just to start just about where we were, it is important to note that if this is the case, then we would be able to see that the sun and the earth function the same because each are the same general central object. In fact, if the universe is infinite, then all, quote, central objects must function the same. A very similar process can be conducted to determine whether or not there are parallels between the systems that indicate if this is the case. First, the sun has the following characteristics. 1. A photosphere, the outer shell from which light is radiated. 2. Emissions largely in the visible light spectrum. 3. Sunspots form in the photosphere. And 4. Solar flares emit from sunspots. The question becomes, does Earth have the same characteristics? The Earth is a smaller mass than the Sun. Generally speaking, even though systems function the same, the rate at which they function relative to other systems is dependent on their mass. For example, a planet orbits the Sun much slower than an electron orbits an atomic nucleus. With that in mind, the Earth has an outer shell from which light is radiated, as seen in Figure 14. This is known as the air glow of the ionosphere. So, while the sun emits in what we see as the visible light spectrum, this is a function of the mass of the sun. For the Earth, the emissions instead are in the infrared spectrum. This is because the Earth is less massive and therefore its emissions are less energetic. If we consider the opposite direction, that of a significantly more massive object than the sun, then this indicates that a sufficiently massive object would emit beyond the visible light spectrum and instead be seen as emitting in the X-ray spectrum. This concept is centrally important to the understanding of black holes. When it comes to sunspots and solar flares, the positioning of sunspots at the edge of the photosphere is an important aspect of these features of the sun. If the same structures exist on the Earth due to the relative mass difference and the faster rate by which smaller objects generally function relative to larger objects, then we would expect these to be more difficult to see and more rapid and at the edge of the air glow of the ionosphere. Large thunderstorms on Earth are capable of producing various electrical phenomena known as elves and sprites. Elves are disk structures that can be detected at altitudes of 100 kilometers above the Earth. These form specifically over thunderstorms. Sprites are electrical discharges which occur above thunderstorms as upward lightning. Specifically, sprites arise from a thunderstorm and consist of filaments which eject outward from the confines of elves as shown in Figure 15. Functionally, elves are Earth's sunspots and sprites are Earth's solar flares. In other words, Earth is a star. This brings us back to black holes. What this analysis suggests is that these objects function no differently than any other that we observe. Why then do they appear to behave so extremely? Since their discovery, the description of the nature of black holes has been built upon the years of speculation leading up to that point. It is taken for granted that black holes are black holes to begin with, specifically that they are singularities from which nothing can escape, as this description finds its origin even before they were observed. Thus, the first step to understanding how black holes have been interpreted, just as with the systems above, is to look back through the history of interpretations that led to current outlooks. This process enables consideration of the thought process that has been used, which exposes where assumptions were made. Before these objects were known, the first step in the process of their interpretation was the description of gravity by Sir Isaac Newton. From this, in the 18th century, John Michell and Pierre-Simon Laplace theorized that if an object was massive enough, then the escape velocity would be greater than the speed of light. This meant that even light could not escape such an object. Fast forwarding to the 1960s, John Wheeler helped to popularize the term black hole assigned to such a body. This was used to describe such an object where light could not escape its force of gravity. Up until this time, no observations had been made that provided the critical supportive evidence of their existence. In 1971, Cygnus X1 was identified as the first object recognized to be a black hole. Since then, their existence has been confirmed by many observations. Their interpretation, though, has included the same foundation throughout. This basis has shaped how we describe the nature of these objects ever since. It has been taken for granted that black holes are singularities due to our inability to visibly see them. This is compounded by the speculative proposals of their existence prior to their observation, which included descriptions of the nature of these objects. With this in mind, the most important observation about the nature of black holes, defined as singularities, that has been overlooked is the X-ray light originating from them, as shown in Figure 16 of Cygnus X1a, or X1. So this is an X-ray image where we see what appears to be a star-like object. The X-ray light from a black hole is specifically interpreted in current scientific models to be emitted by the gas surrounding the black hole. It is not interpreted to be the actual black hole itself. This is because the objects were already concluded to be singularities, and so when we found objects we could not see in the visible light spectrum, we interpreted that they were these theorized systems, and thus concluded the X-ray light must come from surroundings. In reality, all systems function the same. Just as how Earth is a star, so too is a black hole. Rather than the above image being from the surrounding gas, instead it shows the actual photosphere of the black hole object. In addition, due to its higher mass, it releases radiation beyond the visible light spectrum. Instead, it radiates in the X-ray spectrum. As a result, when we look at the object in the visible light spectrum, all we see is a gravitational anomaly and no object. This is not because the object is a singularity, but because we are looking at it in the wrong spectrum. In the X-ray spectrum, we see it as it is, a luminous, voluminous body in space, just like any star or planet. This brings us back to the observer composed of smaller particles looking at our solar system and seeing a galaxy. They see the star as a black hole because the mass ratio of their particles to the emitted radiation makes it appear in the X-ray spectrum. When they look at the sun in their perceived visible light spectrum, they only see a gravitational anomaly. A smaller observer still would see the infrared radiation of Earth as X-ray radiation and would see Earth as a black hole. This touches upon the nature of light. There is an infinite span within the electromagnetic spectrum. This span does not just arbitrarily exist, but for a given observer, they see each wavelength as they do specifically because of the mass ratio of their building blocks, atoms in our case, to the mass of the particles of which the light is composed. Light is not massless, but rather is so perceivably low in mass that we cannot detect the difference. The entire electromagnetic spectrum arises from the differences in the mass of the particles emitted by a given source. Lower energy radiation, such as radio waves, are lower energy specifically because the particles of which their light is composed of are lower mass, while higher energy radiation is composed of particles of relatively higher mass. Thus, when an observer's building blocks are different than our own, the same mass ratios of their building blocks to the particles of the light they see will dictate which systems are seen as which variety of light, or even if it is seen as light at all, or even as atoms, planets, stars, black holes, or beyond. This is because the above parallels allow us to use pattern recognition to deduce that this functional equivalence continues outwardly to infinity. If we could look at any system using any mass particles having the same mass ratios as our atoms to what we see as galaxies, solar systems, or planetary systems, then we would see the system as the same. In order to interpret how smaller particles interact, therefore, then it is beneficial to extrapolate from this analysis to glean information regarding everything we cannot directly observe, so that our descriptions are built on more exact understandings and less approximations. Alright, so that's the end of the first section of chapter 3. I'm going to go ahead and cut this video, and I'll be back with how electric charges are caused in the next video. Thanks for stopping by and hearing me out.